Hello, everyone. My name is Brogan, and today we are going to be going over the AP Chemistry formula sheet in order to dissect it so that we can know how and when to use each one of them, and also a little bit extra along the way. First of all, it's important to realize why this matters. So these equations that are on this formula sheet, which I have in my hand right now, are more than just equations because they're helpful for deciding what you need to use and what methods you need to do in order to solve a problem. And in order for them to be helpful in the first place, you can use units and conditions outlined in the questions that you're looking at in order to figure it all out. First of all, let's talk about the periodic table itself before looking at the formula sheet. So hopefully you already know that the atomic number right here shows the amount of protons that it has. The atomic mass on the very bottom shows its molar mass, so each one of its moles is that many grams. Metals, such as the ones like here in the middle, they form cations, while non-metals, such as the ones over here and on the right side of the staircase, form anions. So, and then there's also the trends associated with this chart itself. So electronegativity increases as you go up into the right of this chart, and it peaks at, I'm gonna say fluorine. I don't think it's fluorine though. Is it fluorine? I think it is fluorine. Yeah, fluorine. Atomic radius peaks at francium down here. As you go to the bottom and left of the chart. Um, and then ionization energy peaks at helium. So electronegativity ignores all the noble gases, while ionization doesn't, and so that's why helium is where it peaks at. And then you also have to know diatomic elements. So that would be H2, or I guess hydrogen, because it makes H2. And then there's this little section right here, kind of makes a bit of an L shape, like like how you move like a knight in like chess or whatever. So we have nitrogen, oxygen, fluorine, and chlorine. Am I getting fluorine right? I feel like, yeah, I think it is fluorine. Yeah, so yeah, fluorine. So yeah, those can all make, those are all diatomic. So N2O2, F2, Cl2. And I may come back to this section to add a little bit more, but I think right now this is good. Right? Yeah, I actually forgot. And then also the charges. So we can go based off of the numbers on top here. So these over here are +1. These are our ionic charges. +1, +2, +3, plus or -4, and then -3, -2, -1. And then these are all 0. So yeah, you can go, 1, 2, 3, 4, and then it's just, and then it's just sort of backwards. So they both meet at 4. So then it would be 3, 2, 1, 0. So I think that's it now. I think I got it. Um, Hold on. Right. Yeah, sorry. Okay, I'm back now. So, um, there are 11, oh wait, all of the noble gases plus the diatomic nonmetals we've already talked about are gases at room temperature, I believe, while bromine, this one, and mercury, which is Hg, which is somewhere on here. Oh, it's right there. It's 80. They are liquid at room temperature. Everything else is solid at room temperature. That's about all you need to know. I think we have everything covered now. Next one. Okay, so for must know polyatomic ions, we have these nitrate ones, like NO3 and NO2, nitrate and nitrite, sulfate, SO4 and SO3, both are 2 minus. Carbonate, we have CO3, I think. Yeah, that's CO3, which is 2 minus, and then HCO3, which is minus, which is bicarbonate because it has the H there. And then we have phosphate, which is the phosphate family. We have PO4, which is 3 minus, and then like usual with the whole hydrophosphate, it's +1, so yeah, it's only 2 minus, and then dihydrogen phosphate, which is H2PO4, and it's only -1. Yeah, these are very important polyatomic ions. You should memorize these for the AP exam. Woohoo! Okay, so first of all, we need to talk about atomic structure. So this is the section with literally just 3 parts, and they're pretty basic. It's not too big of a part on the AP exam, but essentially, you just need to know that energy is equal to Planck's constant, which is given to you, times frequency, and that the speed of light is equal to wavelength times frequency. So you're going to need to know how to like reverse that equation. Like if you were to divide by like frequency in that equation, then you'd be able to find wavelength by just by having frequency. And the other way around, if you divide by wavelength, then you can find frequency just through wavelength. So, you could find one with the other. And then there is the F-Coulombic equation, which is useful for finding out the force between two. Yeah, okay. So this talks about the strength of the force between two charged particles. So this is the charge of one particle, this is the charge of the other one. And if they're big and they make a big number, then that means there's a bigger force pushing them together. And then you also divide it by how far away they are from each other. And since it's squared, that means that it's like if they're pretty far apart, then they're going to be like a really weak force between the two. But yeah, that's really about it. Just remember, big charges, small distance, big force, bringing the two together, and the opposite, if not. So yeah, not too complicated, honestly. And so, if I had to say what's missing from here, I guess it would be like finding wavelength. Sorry, I'm going to be drawing on here now. Is equal to C over V, and yeah, and then V is also equal to E over H. And yeah, just things like that where, you can solve one variable by singling it out and then getting the other ones. So, yeah, those are the missing ones. Now we're getting into longer ones. So this is the gases, liquid solutions one. So the first equation is saying that the pressure volume multiplied to each other divided by the temperature of one like substance is equal to the same thing of the other one. So this is for whenever, I'm sorry, I shouldn't have said another substance. It's the same substance. So if one of these variables change, that means the others have to change as well. So if V were to decrease, then that means P would have to increase, and if T were to decrease, that means that the top two would also have to decrease. Yeah. So essentially you're just solving, you'd mostly just get like every variable except for one in this, and then you just have to solve for one of it, so it wouldn't be too hard. PV is equal to nRT. This is pressure times volume is equal to the number of moles times the gas constant. You got to make sure to look out for those units. Make sure they cancel out, check them just in case, times the temperature, and you would do it in Kelvin no matter what. Temperature will always be in Kelvin. Make sure temperature is always in Kelvin for almost all of these equations, unless explicitly stated. So, yeah, PV is equal to nRT. That is very important. You could also solve for just P or just V if you divide by one of these to the other side. So V is equal to nRT divided by P, all that. And yeah, okay. Okay. So I may have cut out the previous part, but if I didn't, I misexplained this equation here. PA is equal to P total times XA. I thought the A meant absorbance because it says A is equal to absorbance over here, and it has a little tilted A, but it's not. This is saying that the like pressure of one substance is equal to the total pressure of all substances in like the P total, which you see down here, times XA, which is the mole fraction where it's moles of A, so how many moles the A substance has, divided by the total moles of every single substance in this list, which makes sense because we are trying to find a part of it, and so this is the fraction of what PA is compared to everything in P total. So it makes sense that multiplying P total by the ratio would get us PA, because P total is just all of them added together. The next one is number of moles is equal to mass divided by molar mass. That makes sense because this is just grams and this is grams per mole. And so, it like cancels out and then it's just moles. And so that makes sense. This is, remember, molar mass on the formula sheet. So, you get the molar mass from there. Not too hard. Density is equal to mass divided by volume. You should know this. How much mass per like a specific unit of volume. Yeah. This kinetic energy is equal to 1/2 mv squared, where m is equal to mass and v is the velocity. Yeah, I mean, I don't really know. I mean, if you're given mass and you're given velocity, you know the exact amount of kinetic energy applied to it. So, if it's less mass, then you need less kinetic energy for it to go the same speed. Yeah. And molarity is equal to moles of the solute divided by liters of the solute, which is like, yeah, I mean, that's what molarity is. It's moles per liter. Hopefully, if you're going to the AP exam, you know that. It's very useful. You have to know it for like every single equation and like um all of the reactions that we're going to be looking at for like equilibrium. So, and then this next one is pretty interesting. Um, it is absorbance. It was what we were talking about before, but this is actually absorbance. It's just structured horribly. It is equal to molar absorptivity times path length times concentration. So, so I think from what I've seen in AP problems, this is only really used for how we describe PV over T is equal to PV over T. So if, for example, path length were to go down, concentration would go up, and molar absorptivity would go down. All the B and C would go, B or C, or maybe a mix of the both would go up. So essentially, you just have to know, though that doesn't really change. It's mostly just B and C. If one goes down, the other one goes up. And yeah, I mean, it's not really this. It doesn't really appear that much on the tests, but you still got to make sure that you know where to find it, and that's what I'm here for. So that is it for gases and liquids and solutions. So let's go to the next one. For here, what I'd say is missing would probably be something like P, just this same equation, but except without the T. because a lot of the times temperature is a constant, and with just one of these changes, then you just have to solve for one. So it's just a simple equation. Or it could be, P1 over T1 equal to P2 over T2, all that. Yeah, everything else here is pretty simple, I guess. I guess you could say PA divided by XA is equal to P total. That's an equation that's not on here technically, but yeah, most of these like missing equations are just things that you just get by moving elements around. Oh, and also not sure if I mentioned this, but make sure you use the correct units for the gas constant. Most of the time, you're probably gonna be using this 0.08206 because you are using volume because there's liters instead of joules, but just make sure you're paying attention to those units, or because they could trip you up. Really sorry. So these three equations right here are actually for the orders. So this only works if your equation is in first order. This works if your equation is in, sorry, this is zero order. This is first order, and this is second order. So that is the power at which your concentrations are at like a overall. So it's like rate law is equal to K A the power of M times B the power of N, and you find these. It's not on your formula chart anywhere, so hopefully you may have to look into it if you figure out how to do those. It's the rate of change. You got to cancel those shit out. We don't have. Oh my god, I cursed in the video. Cancel it out. And yeah, so this is half-life. This equation's half-life. And that means that it essentially means that at that point, dependent on the rate constant, is whenever your initial substance is halved. So it's as your concentration is decreasing, that is the point calculated by this for whenever you have half of whatever substance you put in. So, oh my god. So that means that whenever you have a large rate constant, then that means that you get to half-life sooner. And the opposite for a smaller rate constant. So like if you had a decimal rate constant, then that means it would take longer than 0.693 seconds to get to that point. Well, if you had a very large rate constant, then you divide 0.693 by a very big number. That's a very small amount of time in order to get half of your original amount. Okay. And that's about it for this section. We still have not gone on to the biggest ones yet, so strap in. So these equations only work if there is no B and it's only A. And so that means if M is to the power of 0, then this works. If M is to the power of 1, then this works. And if M is to the power of 2, then this works. That's why. So it's 0 order to the power of 0, first order to the power of 1, so on. All that. Okay? That makes sense, right? Okay. Also, this equation, this half-life equation, only applies if we are in first order. Okay? So these two are linked. And there's a lot of scribble on here. But that's just because I didn't want to. You can't draw in there, and there isn't really much room out here. So, yeah. And that's about it for this section. And we haven't even gotten to the big parts yet. So, strap in. And now this section, there honestly really isn't much missing except for the whole rate law thing. And yeah, I'm gonna be honest, looking back at this is a really big mess, but yeah, it's pretty self-explanatory. There isn't really much you could do with these equations. Just know how to find the m and n for a and b respectively, and then you'll be good. So I guess just a in this case. No, there won't be a b. Okay. Oh boy. So this is about equilibrium. All of these are about equilibrium constants and all that. So let's just get started here with equilibrium constant for molar concentrations. So this is the products to the power of their coefficients, respective coefficients, divided by, oh yeah, they're multiplied, divided by the product of the reactants to the power to their respective coefficients. And this is in order to find the molar concentration, which is the ratio of products to reactants at equilibrium. And so whenever Kc is met, that means whenever Kc is equal to Q, and Q is, hold on. Yeah, Qc is the reaction quotient, which is calculated the same way Kc is, but Kc is where you're trying to get to. This is where actual equilibrium is, while Qc is the current moment. And so, if Qc was less than Kc at that moment, then you'd want to bring it upward by getting more products and less reactants in order to reach Kc, which would be equilibrium. So Qc is where you are, Kc is where you want to be, and same goes for all these other ones, like Kp, that's basically the same thing. It's the products pressure to the power of their coefficients multiplied together, divided by the product of the reactants pressure to the power of their coefficients. Same thing. Not that interesting, really. But I don't even know why I wrote this equation twice, huh? Yeah. And what else? So Kw, so we know that the equilibrium constant for water is 1e negative 14 at ideal temperature, 25 degrees Celsius. And Kw, which is, yeah, it's just 14. It's just another thing for water. And it's just pH plus pOH, and pH is equal to negative log of H3O. And right before we talk anymore about, in all honesty, like the most boring things, possibly ever, I do need to explain that there is a formula to convert Kc to Kp and the other way around. So Kp is equal to Kc times RT times the number of moles. Which means that the equilibrium constant for concentration, which you can calculate, multiplied by the gas constant, which is on your formula chart, times the temperature, which is in Kelvin, once again, to the power of the change in moles. So it would be moles of your product minus moles of your reactant is equal to Kp. And so this equation, as far as I've seen, is not on the chart, but it should be because it's pretty important and we use it for a lot of problems. I'm not sure exactly how many times it would be on the AP exam. I assume not that many, but it's still something that we have to learn to use. So I'd assume it would be on the AP exam. Okay, so let's just get over a few things. If pH is less than 7, then it's acidic. If pH is more than 7, then it's basic. And if pH is equal to 7, then it's neutral, like water. Um, these equations are all basically used to find pH, and this is used to find pOH. You get the molarity of an equation where it's like one substance HA breaking down into two parts, one of which one has a positive charge, the other has a negative charge, and you use a Rice chart in order to find X, which is how much H plus there is, or OH minus, because this is basically H plus, by the way. I know this is H3O plus. It's H plus. Actually, I guess everything on here that's normally H plus is actually written as H3O plus. But yeah, through the Rice chart, by having given to you the Ka, they're mostly going to be given the Ka. If you're not given the Ka, then you'd have to find it through the Kw and the Kb, possibly. But yeah, you have to use a Rice chart, and then you can find H plus, and then you can find pH through that by plugging into this equation, just to find out whether it's acidic, or if it's basic, or if it's neutral. Everything here is about acid, whether it's acidic or neutral. And this equation down here is very strange. No, actually, first of all, these are like, it's like balance. You know how we know like Kw is equal to H3O plus times OH minus. It's basically just that again. And if they're all in like P form, which means that it is equal to 14 at normal like standard temperature. But if it's not standard temperature, then it's this. You gotta do all this. And yeah, P form is just whenever it's negative log, which is great for Ka and Kb. Yeah, I mean, I don't even think this shows up in the AP exam that much. I'm gonna be honest. You don't need to worry too hard. You don't need to worry too hard about this. But if you want to worry about it, it's on here. And pH is equal to pKa plus the log of the concentration of A minus over the original broken down thing. And A minus is basically the same concentration as H plus in this equation. So that's great. Yeah. Um, let's just go on to the next one. Hopefully the next one will be a bit more useful. And for this, we already touched on this is a missing equation here. And QC is also missing here as something like a defined thing. Even though you have to know what QC is, or what Q is for a lot of these things. So yeah, this is our missing equation for this part. Okay, now we're discussing thermodynamics. This is the last section that we need to talk about. Woohoo! Okay, so first of all, we have heat, which is equal to mass times specific heat capacity, which will be given to you, times the change in temperature in Kelvin. So, yeah, if it's like everything else. If like heat goes up, or if mass goes up, then heat goes up, and you could solve for one of these if you're given everything else by just like dividing. Really not too difficult. Not really. This will only show up a few times, and it'll be like a free gimme question, or maybe it'll be like on some random FRQ, and it'll be like part 1 of 1000. Who knows? And then we have these, and these are very, very simple. It is just finding standard enthalpy, standard entropy, and standard Gibbs free energy, which it'll mostly be like an FRQ, and they'll give you the standard entropy of like each individual part, and then you gotta like multiply them and by how many like moles there are of it, and products minus reactants in order to find the change in them, and which is really useful for this equation. So you can, most of the time they will not give you this. They'll just give you these two, or you'll have to like get these two or by some like random contrivance or something. And you will have to find this, and then they'll ask you a few questions on it. Like if it'll ask you like at what point does the reaction become spontaneous? So and so if change in G is equal to is less than blah, if change in G is less than 0, that means it is spontaneous, and if it's greater than 0, that means that it's not, which is sad. So yeah, and you got to remember this minus sign. So if you have temperature will never be negative because this is Kelvin, and it's literally Celsius plus 273. And if I don't even think it's possible for us to go to 0, let alone a below 0 for Kelvin. So that's pretty assuring. So yeah, if you had a negative, I could actually make a little chart here. Hold on, let me make a little chart. So for change in heat and change in temperature, if change in heat is a negative number, while but oh my god, Jesus Christ, standard enthalpy is a negative number, while standard entropy is a negative number. That means that this equation will eventually become non-spontaneous as temperature increases, because we're subtracting a negative number, which would be adding to standard enthalpy, meaning that eventually, as temperature increases, if it hasn't already been positive, it will become positive because temperature can forever increase, and that means that we'll be adding an infinitely big number at some point. And let me just add another section here, actually. If change in temperature is negative, but oh my god, I'm sorry, I keep messing this up. Well, if standard enthalpy is negative, while standard entropy is positive, then it will always, forever, be spontaneous, because we'll never go underneath, or we'll never go above, I guess, the negative standard enthalpy that we already have. And so, if standard enthalpy is positive, while standard entropy is positive, that means that eventually we will become spontaneous past a certain temperature, because eventually we'll subtract enough to be in the negatives, because we're at the positives whenever temperature goes to 0, but as temperature increases, we'll subtract a bigger and bigger number, because we're subtracting a positive number multiplied by another positive number. And finally, if standard enthalpy is positive, while standard entropy is negative, then that means that we will forever not be spontaneous, because we start with a positive number, and then as temperature increases, we get an even more positive number. So we will forever be non-favorable towards a spontaneous reaction. Okay. And then here's other ways of calculating standard Gibbs free energy, such as the negative gas constant, which is given to you, times temperature in Kelvin times natural log of the equilibrium constant. And you already know the equilibrium constant. You know how to find the equilibrium constant. We know that. It's what you're looking for. It's at that point is whatever. It's all equal. So yeah, that's very useful. And then finally, standard Gibbs free energy can also be equal to negative number of moles of electrons. Okay, so you'd have to count the moles of electrons. You'd have to like balance out the equation and get the get like both elements together, and then you'd have to like separate them, make sure they're balanced in both charges and in elements by adding electrons and water and hydrogen, and then multiplying them out so the electrons cancel out, and the amount and the number of the electrons that you cancel out, that is the number of moles of electrons that are in the formula, times I think it's Faraday's constant, which is given to you, times the standard potential of the equation, which you calculate this by, sorry, just had to check something. It is E of the cathode minus E of the anode. And so, what that means is that if you were given two things where it's like E degrees equal to like plus like 30 through like 0.03 but 0.3, and E change is equal to like negative 0.7, that you would do 0.3 minus negative 0.7, so you just add that plus that flipped, and E cell, which is this, would be equal to 1. And so I don't think in the entirety of AP Chem, unless it's like a trick question, this is going to be a negative number. So if you're given two standard like E like degree symbol, and then from an equation, all you have to do is just make sure that you flip one in order to make it to where if you add them together, it's a positive number. That's all you have to do. It's very, 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 very simple. And this one is just like, this is just like another plug-in sort of thing. It's just current is equal to charge divided by time. Like, great. It coulombs per second is equal to amps, if you're curious. I think it says that in the very front of your formula sheet too. And this next one is if we are not at standard conditions. So it means it's just like it's so long-winded. It's so like, okay, so this is what we've just found. This, these added together get 1 minus gas constant times temperature in Kelvin divided by number of moles of electrons. Remember, I already talked about that. Times the constant, which we already have, times, these are in a fraction, by the way, times the natural log of the reaction quotient, which is the current ratio of what we were talking about a long time ago, where it's products over reactants, and they're each of their power of their own respective coefficient. Okay, that about covers this unit. So yeah, a lot. It's just a lot. For this, E cell is equal to E cathode minus E anode. That's our missing equation for this. Also, whether like how determining spontaneousness from standard Gibbs free energy change, and also finding E cathode and E anode in general. That's also something we figured out. And also, you can move this around, so it would be like I times T is equal to Q, or Q over I is equal to T, just random stuff. Like, I guess that's technically missing. Okay, so this is a section that's on the rubric here. When we need to talk about 8 examples of whenever it is like saying something and you need to know where to refer to. So, if it mentions grams and liters, then it's probably going to mention, then you're probably going to have to do something regarding molarity, which is moles over liters. And so you may have to calculate you may have to see like the number of moles, and then you're going to have to calculate, well, I'm sorry, you're going to have to calculate the number of moles by like dividing grams by the molar mass in order to find the number of moles, and then divide that by the volume in order to find molarity. Grams plus milliliters, that's going to be something probably regarding density, which, as you remember, is mass divided by volume. Mass, volume, density, grams per milliliter. Pressure plus temperature, you're probably going to have to talk about gas law, which is the equation where, let's just go back to it, PV over T. So yeah, it could be something like this, where something changes, pressure and temperature, that's still like another ratio. So if one were to change, then the other would have to. It's either that or just volume would change, though if it just mentioned pressure and temperature, then it would probably also explicitly state that the volume was constant throughout the entire thing. And so if it mentions pressure and it mentions temperature, think of the gas laws and all that. So if it mentions pH, go back to this. All of this is so pH. Like, it's insane. If it ever mentions pH, just go look at this. Once pH, it probably wants you to do this big long-winded process where you got to find this, and then you get these two, and then you got to find this, and then you got to do this, and then you get this, and then you get this. It's a long process. It's just so boring. If it's talking about like a rate table, then it means it could be like this. We talk about calculating the M. That's what a rate table. That's how you're gonna find that, by getting like ratios and seeing the rate of change. Because if it was like, there could be like a constant rate of change, or it could be like a compounding rate of change, like a quadratic on like a chart. So yeah, think of that. If you see a rate table, immediately go to this kinetic section and just try to figure out which one of these equations you use. If you see change in H, it's definitely going to be talking about thermodynamics, because it's going to probably be referring to standard enthalpy, which is going to make you do all of this and all of this, and there's this, and oh my god. And then voltage, it's going to be about electrochemistry, man. It's going to be about this. It's going to be about this. It's going to be about this. And then concentration shift, it's going to be about equilibrium, which, is this. Because concentration shifting, that probably means that's, either going towards or away from equilibrium. Or equilibrium like shifts, because you need to recalculate this and see like which way it would go. Like if there's more, like if it's like shifting, if there's adding like more substance to the product side, that means it's probably going to shift to the reactant side in order to balance the equilibrium. So yeah, it's and those are just 8 things where if you see this, think this. I hope you guys enjoyed this video. I may have to go back and like look through all of this, because this, like, I'm pretty sure it's gonna be like at least 20 minutes long. Maybe I'll cut some parts out. I don't know, but I hope you guys really enjoyed it, and I'll catch you guys in the next one. Goodbye.